Okay. So, just get a reminder where I'm at in memory, or where I'm at in my material. So, the most important thing to take away from understanding what the stack looks like is that your local variable, the password buffer, and this meta, like basically process meta information is the best way to think about this, say DBP and the return address, are stored in the same vector of memory. All right, so these are kind of all in the same playing field. So if this, instead of being, 1, 2, 3, 4, 5, 6, 7, 8 characters, was 70 characters, we would override some of this stuff, and that would kind of cause havoc with our program. What I want you to do is actually open up the program in the debugger. So the easiest thing is just to type quick in GEB, and then put it in the debugger again, GEB simple login again. And we're not going to set any breakpoints this time, okay? Just kind of run the debugger and hit R for run. And this time when you enter your password, I want you to press down the A key and just keep on holding on like crazy. Just put like 200, 100 characters in there. Just let it keep scrolling for a while. Okay, so what's going to happen when I press enter here? Anyone that hazard a guess?
You just overflowed everything.
Yeah. So this is what you want to see whenever you're looking for a vulnerability. You see that EIP equals 414141. Yay! That means you're, half the battle is done, basically. So you got this crash, and basically what happened was I explained it in my slides best. I put in a whole bunch of A's. Our password attempt was interpreted as capital A, capital A, capital A. After a while, we were outside the bounds of our 64-byte buffer, and we overrode the safe frame pointer with AAA, and the safe return address with AAA. And then we went to return back into the main function. We tried to use AAA as our return address, and we got this crash. Now, can anyone tell me why exactly we got a segmentation fault and why there was a crash there? Why did this crash? I mean, sure, we overrode return address, but what is that?
Yeah. Why does it jump to location 414141? Sorry, excuse me.
And why was that a problem?
Well, we don't know what's in there. It's probably just garbage or
It's
something.
not even allocated. Yeah, that address is totally bogus. So that's why you get the crash, because it's trying to use OX414141 as a EIP, and that address isn't even valid in the process address space at this point.
Is that what specifically is a segmentation fault? Trying to go to an address, or is it?
Yeah, basically. Okay. So to give you a better understanding of what happened, let me re-step through that. You guys don't have to do this yourself, you can just follow along. I'm going to set a breakpoint for after the gets call again. So for after I, clobber the stack with all those A characters, and I can just sort of show you what's going on. Also before and after. So authorize plus 27 and authorize plus 32. Feel free to follow along if you want, or just look at what I'm doing. Okay. So this is before I've entered in my password attempt. I'm checking out my saved frame pointer, my saved return address, so both of those are still legit. They look good. C to continue. Wow. For those of you that already feel pretty good at this material and are on board at this point, I'll say that you can actually gain arbitrary code execution by just overriding the least significant byte of the saved frame pointer. So if you already feel pretty good at this material and are getting bored, you should think about how you would actually accomplish that. Okay, so back to this. Entered in all these A's, should have covered the stack. Let's check out the saved return address again. Okay, so these are both overridden with AAAA. Those are bad addresses. They're not even allocated in the process address space. Whenever the processor tries to use them, we're going to have all kinds of problems. Now let's see exactly where the crash happens. And it's actually right at this, this return statement. Basically what return does is a mnemonic for like pop EIP, pop off the stack into EIP. And at that point, the stack will be pointing at OX41414141. That was where the saved return address was. So where is the stack pointing at right now? Let's check it out. Right before this return statement is executed. It's pointing at OX414141, so basically overrode most of the stack with OX414141, which is the hex code for capital A. The return instruction is going to do essentially pop the EIP. I'm going to continue. I get the segmentation call. So that is the basic mechanism we're going to use to gain arbitrary code execution for at least the first half of this day. And how's everyone feel at this point? Bored? Confused? Happy?
That's fine.
Making sense.
Okay. Making sense to you guys in the room? Remote users? All right, so shortly we'll be embarking on some do-it-yourself labs. And I hope you guys enjoy this. Our first lab is going to be exploiting the simple login program. And essentially what we're going to do is we're going to overflow the password attempt buffer, and we're going to point the return address basically successful password attempt handling code. And so then no matter what we have entered for our password, even though it was totally bogus or a bunch of A's, we will still end up executing the successfully logged in code. Okay. And this is how we're going to do this. Step number one is figure out, okay, we know that we can overwrite the return address, and that the return address will eventually be put into EIP. What do we want to overwrite the return address with? Overwriting with OX AAAA is cool, but it's not really useful. So we actually want to find an address to replace the return address with that is useful to us. And so if we go back and look at the actual function code, we can see that if authorized is successful, luckily it has this handy-dandy Go shell function, which will spawn us a shell and print us a nice successful message. And so instead of returning into AAAA, or instead of returning into this if-else handling code where it normally does, we want it to return into the Go shell function. Because luckily this nice simple login program has a function available for us that will spawn us a shell and all that kind of handy things. And that's unrealistic, right? But is it? As we'll see later on, it's not. Oh, yeah, day two. Got your minds wondering already. So at this point, I want you guys to try to find out what the address of Go shell is. So what is the actual hexadecimal address that we should overwrite the return address with? So let's see how everyone's feeling with the debugger. Let's see if we can get that address for me. Yeah, go for it.
So I did you just symbol name is 08, or no, it's 0x04H288.
Okay. So everyone got that same address? And that's basically Go shell plus 0, the very first instruction. And so the way that they presumably did that, I'll just show you guys on the web, so you know. If I was trying to find this address, I would load up the program in the debugger, and then just do disassist Go shell, And I would just say, okay, the very first address associated with this function is that top one there, 08048288. This always makes me feel more comforted when I get nervous because I feel like I'm not explaining something very well. Just holding the stick, makes me feel calm. Okay, that's okay. I don't need to be calmed down right now because everyone understands the circuit. So that's the address we want to overwrite the return address with. For those of you that are feeling bold, I challenge you to go ahead and try to, actually no, we're not at that point in this class. Let's just step through this first lab together, and then you guys can be more on your own. Okay, so we want to build a payload basically to use our password attempt, so that instead of entering in the password, we're going to enter in a bunch of A's and then that return address, the 0804 address. That's going to overwrite the return address with the first instruction of Go shell. Then when the authorized function returns, we'll be executing the Go shell function instead of returning the name. So to do that, we're going to build our exploit, our first exploit in the class. And the first thing our exploit needs to contain is some amount of A's. That way we completely consume the password buffer and can start overwriting that process meta information. So who can tell me how many A's we will need to enter in first before we actually write the return address? How many A's do we need to consume the password buffer? 64. And how many bytes do we need to write in total before overwriting the return address? 68. Yeah. Because it's 64 bytes will completely consume the password buffer. So all of this is 64 bytes. Then we're going to run the save frame pointer. At this point in the class, we do not care at all about the save frame pointer. We're going to just completely overwrite it with jump. A is totally fine. In some exploits, you'll want to control that value. In this case, we're completely okay with just corrupting it because we will use the return address as PIP before we even try to start using this. So it doesn't matter if we completely corrupt it because we will gain control of PIP before this corrupted value comes into play. You guys follow why that doesn't matter? Just know that we don't care about what this is right now, so we can just override it with AAAA. So, and it has to be 4 A's, right? Because each one is 8 bits, and that's a 32-byte value, or a 32-bit value, excuse me. One thing that might help you, though, is instead of overriding this with A's, make it B's instead, or something like that. That way, it just helps you figure out if you're doing something wrong. If you see A, B, 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 and you're saved BBB instead of B, 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 you know that you're kind of off by one, your payload's a little bit screwed up. But you can make it A's, B's, whatever floats your boat. And then we'll need to basically write the return address, which is a little bit strange because up until this point, we're just feeding in that read-in user input function, regular ASCII data, A's and B's, those are totally legit. But then we have to feed it in a return address. And the return address is 080482DF. And none of those really respond to typical ASCII codes, right? That's not something that comes up on your screen like A, B, C, D. But it turns out that we can still send it this sort of random binary data, and it will still accept it. As long as it doesn't contain any specifically bad characters, which we'll talk about later as well. So, our game plan is to build our exploit, which will basically contain 64 plus 4, so 68 bytes of junk, and then that return address that we found. So, okay. Sounds like someone might have their mic on or something. One of the remote students, they dropped it or something. I don't know. Just make sure your mic is muted if you're not using it. Okay, so to build your payload, you can use whatever scripting language or programming language that you like. You just have to basically be able to easily emit hexadecimal bytes of your choosing to basically generate binary data of your choosing. I use Perl for that. I do not know Perl at all. In fact, I kind of hate Perl because I think regular expressions are the devil. But Perl is pretty easy for doing this. So I'll show you guys how to do it with Perl. Bill, could you track down where that awful noise is coming from for me? Okay. I gotta remember how to do this in my Python mode or Perl mode, I forget. Okay, so the first thing we're gonna do is generate 64 bytes of data. We're gonna save this all in a file, okay? And then basically when we run the program, we're gonna redirect the contents of the file to a simple login program. For now, we're just concerned with creating a file that contains what will be our password attempt, which is our exploit. So here's another command that you want to write down. It's easy to get this one wrong since there's a lot of single ticks and back ticks and all kinds of things like that. And I'm just doing a Perl-E single tick print A times 64 single tick. And I'm putting that using this Linux shell operator to redirect the output of that command into a file, which is just what that angle bracket is. So execute this command. Basically, all this is doing is just printing 64 A's. Take the output of this command and put it into the payload file, which is done in container export. Okay. So that's our first 64 bytes. We still have a ways to go since we're going to need 64 plus 4 more bytes for the return address. A very handy command, which you should also write down on your sheet of handy commands, is the xxd command, which will basically just dump the hexadecimal bytes associated with your payload file to the console. That way you can see what your current payload file with your exploit is looking like. This will help you spot problems in the future with your exploit as you're filming. So it'll just give you some output like this, which tells you the offset of, this is your payload and the contents of it. Okay, so that's 64 bytes. That completely consumes our password buffer. Now we need to print add 4 more bytes and save frame pointer. Now before you get too anxious and press enter on this command, make sure you add the extra angle bracket. And this is the append operator instead of the overwrite. If you were doing one angle bracket, it would just overwrite the contents of this file instead of appending to it. You may want to slowly add to it. Yeah, go ahead.
Should it just be 4 instead of 64?
Yes, it should. Thank you. So, I just appended. This is 64 bytes right here. This is basically completely consuming that password buffer. This is going to be the save frame pointer. So we're running with B's for now, you can make it A's or whatever. And then next comes the return address. Now, how are we going to represent this? We can't just type in like Perl-E. Oh, first, let me get that address again. I'm just getting again that address that we are going to use for our return address. Everyone should write this down so you don't forget it. I'm just going to write it on the board for myself here. And it is 0x08 04 82 AA. Okay, so if I was to do something like Perl-E, I'm about to mess up my exploit file, so I'm going to make a bad type. Could I do this? Is that good? Why is that bad?
Little print decimal.
Yeah, because it's going to interpret that basically. You're going to get the ASCII data associated with that instead of the actual binary data. You want to produce the binary version of this string, basically. That's what we're going to try to do. Now, So to produce random binary bytes, like to demonstrate my point, let's say let's just say the address was, you know, BB, 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 CC, 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 CC. All right, so let's just magically say that was what we found should be the return address. And we added that to the payload. So, okay, yeah, let's set the return address to that. Let's check out what our payload looks like now. One obvious problem with this is that, look, we wanted the return address to be CC, but it's 43434343. That's just because that's the ASCII data associated with that. You know, we would want to produce the binary representation of this. Another issue is this is 8 bytes long, okay? And we need it to be 4 bytes long. So to generate binary data like that, you can do it in Perl like so. Okay, so if you add this like \x operator, it's telling me, okay, don't actually generate the binary associated with this ASCII. You know, don't print XAA, XBB. Print the binary representation of this code, this hexadecimal value that I'm giving you. And that's how we're going to have to enter in addresses into our payload. So we can see this time we wanted to generate AA, BB, CC, BB as an address, and it actually ended up in the file as the correct hexadecimal AA, BB, CC, BB. You guys follow that okay? Sometimes that gets people a little confused. Okay, so here's another trivia question for you guys. Let's assume that the return address that we found was AA, BB, CC, BB. Would I enter it into the payload like this? How would I have to enter it in?
BBCCB.
Yeah. And why is that? Little Indian. x86 is Little Indian. Is ARM big Indian or Little Indian? I don't know. You ARM guys?
I think it's big.
Okay, yeah, I think so too, but I'm not 100% on that. So in x86 world, we have to write our memory addresses backwards. And that's because x86 is Little Indian architecture, which means it stores 32-bit memory values, or 32-bit values in general, backwards. Okay, it stores byte-wise backwards, so not each bit. If we wanted this to be represented, if this was a memory address we were trying to get into memory, we would have to write it as DDCCBBAA.
Corey, quick question.
Yeah.
If that were actually that value A, B, B, C, C, D, E, F, then you would write it F, E. You see what I'm saying? If they weren't the same, yeah.
Yeah. Okay, so let's assume the address we're trying to write is OX12,
Correct.
3, 4, 5, 6, 7, 8. Okay, we would actually write this as 7, 8, 5, 6, 3, 4,
That's right, yeah.
1, 2. Okay, and that's because it's byte-wise backwards. All right, each one of those X, 1, 1, or 2, 2, or 7, 8 represents 1 byte, and it's byte-wise backwards. So you can see when I run this command, and look at the hexadecimal values associated with that file, it actually is putting it on the representation as I expected. Notice also, don't get confused that this does still appear in the wrong order in the file, but once it gets loaded into the process's memory, it will appear in the right order, basically. Or it will be interpreted in the right order, is more correct way to say it. Okay. So I think I messed up my my payload file. Yeah. So you people, remote people, shouldn't be having to do this. I just did this because I messed up my payload as part of a demonstration. Okay. 64. This is my password buffer, this is my safe frame pointer. Now I have to write out the binary representation of that return address that we want to change the return address to, which was the 080482AA, which was the first instruction associated with the Go shell code. So let's do that now using our newfound Perl syntax. So the address I'm trying to write is 080482AA. I'm going to do it like so. Backwards, because I'm in a little Indian world here in x86. I use the double angle bracket to append to my payload, not completely overwrite it. It's important. And there it is. This is our final exploit for the simple login program. Completely consume the password buffer, overwrite the saved return address, and then, or overwrite the saved frame pointer, excuse me, then overwrite the saved return address with the first instruction with the Go shell code. And what we're going to do now is throw our exploit at the simple login program and see what happens. So to do that, we want to use the contents of the payload file as our input, as our password attempt. So we're basically going to use some Linux syntax to tell Linux to use the contents of our payload file as the input for the simple login program. There's a number of ways you can do this. One way to do it is just to, I'll show you guys, we'll be using a few different methods depending on the lab we're working on. One way to do it is to use kind of the reverse angle bracket, which says instead of overriding the output of this command with this file, or instead of overriding this file with the output of this command, use the contents of this file, angle it into the input of this program. So we do this, something different happens. For instance, if I'll just say early print, this is a wrong password attempt. You guys don't have to do this. When we get the wrong password attempt, we get, you entered in the incorrect password. But when I sent our exploit at the program, notice that it said, would you like to play a game? But it didn't spawn a shell, interestingly. And we can see if we look at the simple login code that, printing that message is part of the Go shell function. So we are indeed executing the Go shell function as a result of our exploit. Is everyone excited about that? Oh, that's cool. Okay, but let's talk about why a shell didn't spawn. Does anyone know the answer to that? It's actually a little bit tricky. Why didn't the shell appear? Yeah, I'll go ahead and tell you guys because this one is actually really tricky. And it's because when you use like the redirect operator like that, it actually sends like an end of file message as well when it's done reading the contents of the file. So a shell actually is spawning, but the end of file message is basically instantly closing the shell as well. So that's a little bit tricky to deal with. We're not going to be too concerned about dealing with that at this point. I'll show you guys how to deal with it a little bit later on, but just know that you did successfully exploit this login program. Hey.
Sorry, can you just very briefly, the commands after when you like to play man, the set REUID, and I'm guessing the last one, the EXECVE, is what executes the shell, but what those commands are and see.
Say that again, what was the question?
In the Go shell function.
Oh,
What
yeah,
the last two
So you're just curious about the C code associated with actually spawning
Yeah,
the shell?
just the last two lines of the Go shell, yeah, those two.
Yeah. So this was because originally I was going to have this program run as root, okay, and then have you guys get a root shell for doing this. That doesn't matter. Basically, it's just setting your effective user ID to 0, which basically means changing permissions to root. And execve is basically just execute this command. The syntax is a little bit goofy. It's telling you execute this command with these arguments, and yeah, we'll get more into this later on when you're developing your shell code. Just know that that code is just associated with spawning a shell. And you just kind of have to do it that way because that's the way that the Linux system call works. Okay. Would you like to play a game message? Everyone try that? It's important to make sure you can successfully build these payloads yourselves and know the right syntax, because soon you'll be on your own developing these payloads and exploits completely by yourself. And so you want to iron out all the details and problems at this point. So everyone should have been able to generate their payload and then get this message. Okay, so one thing that might be a little bit useful is just to run this in a debugger, just so you can sort of follow along the execution process in the debugger. And this is really just to get ingrained into your head the whole process. That way when we're working on hardware exploits, you are better equipped to debug issues that come up. So let's do GDB simple login, and we're basically going to debug the program with the payload running. And just to prove to you, beyond a shadow of a doubt, that the Go shell function is executing, we're actually going to set a breakpoint for it. And even though we got to it via this crazy exploitation method, the debugger is still going to be fine with what's happening. It's going to be completely oblivious to the fact that the process is being exploited. So I'm going to set a breakpoint for the Go shell function, break asterisk Go shell. We shouldn't hit this during the normal execution of the program, however we're exploiting it, so we will. And then also I'm going to set breakpoints for right before and right after the gets calls, just so we can see the return addresses change. So let me find out what those were again. This is this authorize, right before gets is authorize plus 27, right afterwards is authorize plus 32. Okay, so at this point I've got breakpoint set for the Go shell function right before the call to gets, which reads in our password attempt right after the call to gets. So right before the call to gets, our return address should be legit, okay. Right afterwards it should be corrupted and pointing at the Go shell function. So we can do R, use angle brackets in GDB as well. R angle bracket in our payload file. So run it with our payload. We hit the first breakpoint. Let's check out the return address, x/2x EVP. This is right before our password attempt, so the save frame pointer is good, save return address are still good, they have not been corrupted. We hit C to continue. This will be right after the call to gets. There we go. And at this point, the save frame pointer and save return address have been corrupted. And this 080482AA value is pointing at the Go shell function now. So if we hit C for continue, there it is. We're actually executing the Go shell function. So beyond a shadow of a doubt, you can actually have redirected the control flow of the program by exploiting that password buffer. Password. The shell spawns but then instantly closes because of the end of file message. So we'll figure out how to get around that later on. Doesn't matter for now. Okay. Let me catch up. Okay, I guess I did want to get past that little shell issue that I was just explaining before we go on. This is one to write down when you're working on other payloads or working on, there are some exploit contests where they run into this issue as well, so it's good to remember. To get around that end of file message thing, you can use the following syntax. Now I will explain this in a second once I've typed it out. Okay. So in Linux, the pipe operator basically redirects the output from this to this. Okay, so it's kind of like that reverse angle bracket I was just showing you. So the pipe operator is taking the output of this and redirecting it to this program. So, and what this is doing is first it's entering out the payload file, but then it's also doing this cat dash command, and cat basically reads in data and then echoes it back out. Okay. So in this case, dump the contents of this file, cat this file, dump the contents of this simple login program, but also open up a cat process which reads in data, then outputs it out, and it will keep in reading in your data and outputting it into this process. So what will happen is that we run it, the payload smash the stack, and we're executing the Go shell function, and now we're basically executing this cat and redirecting the output of cat to this program, and cat will take in anything that we do, so like ls, it's reading that in and echoing it out. And since it just keeps on reading in and echoing out, it's never going to send that into file message. So we can just keep on sending commands to shell out this file. Yeah, that isn't too important, but I just sort of wanted to justify why the shell wasn't automatically appearing for you guys. I actually don't think that you guys have to use a syntax.
Do the parentheses put it in the background? Is that what's happening?
No, the parentheses just kind of group both of those commands together, because it basically has to group all this together and send the output of all of this to the simple login, not either of them individually. Okay, so just want to do another morale check and see how people are feeling. At this point, good. Bedford people, feel okay? Remote people, how's the morale level? Sometimes people can get kind of, downtrodden with this material because the debugger can be menacing.
Yeah, could you execute that again and then type ID to make sure you actually are root?
You could, but in this case, the simple login program isn't executing as root, so it would still be your normal user root. But yes, you could do this if this is running as like SUID root.
Okay, I thought it set you to the root user and then gave you a shell.
It did, but it can only do that if if the program is running with root privileges, and I don't have the virtual machine configured so that that process is running with root privileges.
Oh, I see. Okay.
But if you were to do chmod plus S on the simple login program and then run the payload, you wouldn't see that, as long as the process was owned by a root, SUID root.
I see. So you want to try to exploit programs that have this SUID?
Yes. If we're talking about local Linux exploits, that's exactly what you would want to do. You would find out every program on the system that has the SUID rootkit, and then try to exploit those. Or what you could do is, let's assume that your payload file that you generated is used by the root user. We'll say it's like a PDF, okay? If we can get the root user to open up that bad PDF, then he will have executed your exploit as root, and you could have programmed your exploit to add you as a root user.
Okay.
But that's just kind of talking about. That's just kind of other extracurricular information. This is all just sort of the core concepts of how you actually go about the exploitation process. What you're trying to accomplish and what you're trying to exploit will sort of change the process a little bit. I was trying to show you guys at this point sort of the core mechanics of how this works. Yes. So yeah, guys, let's take like a 15-minute break. Or how about, we'll say 10 minutes. We'll let us cover 10 minutes.